In this video, we're going to describe and analyze a basic low-pass filter. Now, low-pass filters are found in many electronic applications. You might use them, for example, for noise filtering or switch debouncing or many other reasons to use them. And there are many types of low-pass filters of varying complexity. You can use active circuits and integrated circuits to make a low-pass filter, or you can make one using simple passive components. In this video, we're going to discuss the most basic of low-pass filters, which is a simple resistor-capacitor circuit. So imagine that we have a circuit, and we have a voltage in to our circuit, and we construct a resistor and a capacitor like this, such that we then have a voltage out over here with a resistor of resistance R and a capacitor of capacitance C. So what we want to know is, given a particular voltage in, which may be a step function, or it may be a sinusoidal function, or it may be some complex combination of these, what do we get for V out? Now, there are easier ways to analyze this perhaps, but we're going to go back to kind of the basic mathematical definition of capacitors and resistors. You know, for example, that for a resistor, a purely resistive load, V equals IR. And in our case, we're going to define the voltage across the resistor as VR, so V sub R. So we'll say that V sub R equals I sub R, the current going through the resistor, times the resistance. For a capacitor, if you remember, the charge on the capacitor, the voltage on the capacitor, the change in that voltage is related to the amount of current flowing through the capacitor. In particular, we know that for a capacitor, I, the current, is equal to the capacitance times the rate of change of the voltage over time. And if we call the voltage across the capacitor V sub C, then we see that, let's see, I sub C, the current through the capacitor, is equal to the capacitance times dVc dt. Now in our circuit, if we assume that there's no current actually flowing out through V out here, or through the leg that leads to V out here, then that means that the current flowing through the resistor is the same as the current flowing through the capacitor. And if we go around the loop and do our voltage laws, then we know that the voltage in has to be equal to the voltage drop across the resistor plus the voltage drop across the capacitor. So using all of these, we can come up with an equation that models our little RC circuit right here. So setting the two currents equal to each other, that means that VR over R, that's from this equation here, is going to be equal to C times dVc dt. That's just setting the two currents equal to one another. And then we know that from this equation here that VR is equal to V in minus Vc. So substituting for the VR over here, we get V in minus Vc over R. And we can take that and rearrange it, taking the V sub C to the left-hand side. We get, let's see, C dVc dt plus Vc over R is equal to V in over R. And we can divide by the capacitance C once again to get dVc dt plus 1 over RC Vc plus, equals 1 over RC, let's fix that, V in. And finally, we note that the voltage over the capacitor is exactly the same as V out, which is what we're looking for. And so for our circuit, we can write that dV out dt plus 1 over RC V out is equal to 1 over RC V in. And this is the governing equation for the low-pass filter that we have created above. Well, that's just great. Now we've turned a nice simple figure into a not terribly complicated ordinary differential equation, but an ordinary differential equation nonetheless. But the important thing here is to figure out what happens when we put in a certain kind of input. What do we get out of it? And the next question is, if we have a step function for v in, so let's say that v in does something like this. It goes along until we get to some point t star, and it's 0 up to that point, and then it jumps up to some value. Again, we'll call this v star. And this may be something, for example, if you push a button or close a switch, v in instantly jumps from 0 to some voltage value. And the question is, what happens at v out in this case? Well, again, you can go through the mathematics of the differential equation, and it's not difficult to show that in this case. So the solution to this equation would look like v out is equal to v star times 1 minus e to the minus 1 over RC times t minus t star. Now in general you can set t star equal to 0 without loss of generality and slide it back and forth. But in our case, since I've drawn the switch being closed at t star, we'll continue with it that way. So if we look at what v out looks like, we'll graph that in red here. Let's see, when t is equal to t star, we get a 0 here, and so e to the 0 is 1. And so we have this right at t star, v out is still 0. As t goes to very large, we get t approaches infinity here, so we get a minus infinity. E to the minus infinity approaches 0. So after a long time, v out is going to approach v star. And then in between, we're going to get what amounts to an exponential function. And it looks like that. And the speed at which, the rate at which this curve approaches v star depends on this value here, 1 over RC. For example, if we wanted to see how long it took for v out to reach 1/2 of the input voltage, we could set v out equal to 1/2 v star. Doing a little bit of rearrangement, that means that e to the minus 1 over RC times the time difference is equal to 0.5. Take the logarithm of both sides and the RC to the other side, and you see that t minus t star is equal to minus RC log of 1/2, which is equal to about 0.637 times the combination RC. So as RC gets larger, then the system response is slower, and of course as RC gets shorter, then you can get a very fast system response.